Unit 6, Lesson 3 continued. Example number 5. Shown below is the graph of the derivative f of some function, capital F. Assume that capital F of negative 3 is negative 8. When they give you something like that, you need to kind of assume that, okay, at negative 3, you are starting out with a y value of negative 8, right? And so if they say, what is f of 2, then you're imagining going from negative 3 to 2. And what would that give you if you started with negative 8 at negative 3? So like I said, it's like the integral from negative 3 to 2 of this f of t dt. And so you're like, well, we were at negative 8 at negative 3, and so then we would add 10 and add 26. And so 36 minus 8 leaves us at a value of 28. And so this f of 6 would be like the integral from negative 3 to 6, f of t dt. And I just didn't like that f, sorry. So again, starting at negative 8, but this time we're going all the way to 6. So we're adding 10, we're adding 26, we're subtracting 8, and then adding 14. Because that one, f of 6, if we know where we are at negative 3, then we have to calculate all the way. And if I added all of those, I should get 34. And f of negative 5 is like the integral from negative 3 to negative 5, f of t dt. But the problem is negative 5 is smaller. So I would say the negative of the integral from negative 5 to negative 3, f of t dt. And so for that one, and you can also, because this one is, since you're starting at negative 3, if you go to the left, you are subtracting, okay? If you go to the right, you're adding, you're adding normal. If it's above the x-axis, it's positive. If it's below, it's negative. When you go from like negative 3 to negative 5, you are, you're subtracting. So this is like negative 8 minus 18. So this one ends up giving you negative 26, which I don't know if this would have made sense. Negative 8. I guess it would have, because you would have started at negative 8. And then you would have gone negative 18. Or would you have started at positive 8 because it's backwards? Anyway, this answer is negative 26. And it might just be easier to think about starting from negative 3 and having negative 8. And then going this way left makes this negative 18. All right, letter D. Since the area under F is positive on the interval negative 3, negative 1, we know that the graph of F must be what on the interval from negative 3 to negative 1? So think about area under it is positive, okay? So that is like increasing. So we know that it is increasing on that interval. And then part E, since the area under F accumulates at an increasing rate, we know that the graph of F must be, and for that one, if it's an increasing rate, you're talking about concavity. And so for that one, it should be concave up. And then the area under F on negative 1, 2 accumulates. So let's look at negative 1 to 2. It accumulates at a blank rate. So F must be blank on that interval. So it's accumulating at a decreasing rate. So it must be concave down on that interval. And then sketch a graph of capital F, show extrema, inflection points, and horizontal tangents. All right, so we already said that F of 2 was 28. We said that F of 6, I didn't circle it, but we said it was 34. We said that F of negative 5 was negative 26. And so now, F of negative 3, they had given us, was negative 8. F of negative 1, that would have been negative 8 plus 10, so that would have been 2. Because if we start at negative 3 and we go to negative 1, we're adding 10 to negative 8, so that gave you positive 2. And F of 4, if we knew that at F of 2 we had 28, and then to get to 4 we subtracted 8, then that's going to be 20. Okay, so now we've got all of these points, and we're going to plot our points. Negative 5, negative 26. Negative 3, negative 8, negative 1, positive 2, positive 2, positive 28, positive 4, positive 20, positive 6, positive 34. And now we have to start thinking about what these values mean. Remember, they said that from negative 3 to negative 1, we have concave up and increasing. And so I know that you could probably go like that from negative 3 to negative 1. We talked about from negative 1 to 2, we had concave down and decreasing. So that one, we could have went like that. And then, and that was concave down. So since it's changing concavity here, this is going to be a point of inflection. And remember that at negative 1 here, you're going from positive slopes of tangent lines to negative slopes of tangent lines. You're going to have another inflection point at negative 3. So this is going to go from being concave up to being concave down, like that. And this is probably more flat here. More like a horizontal tangent. And I know it's hard to show whenever you're trying to. So this is a horizontal tangent at negative 3, right there, where you've got a 0. And there's your point of inflection where it goes from being concave up to concave down. And then over here from between 2 and 4. So you have, it goes from being negative and it still is negative. So that's going to be one of those flattening out type things at 2, because it does not change concavity. But it is undefined there. But so your slopes to tangent lines here are negative, so it's going to still be negative slopes to tangent lines, so it's still going to be concave down. And then this is going to be a minimum. So there's your relative min. There's your relative max. There's another point of inflection at 3, where it goes from being concave down to concave up. So that one's going to be a POI. And I think that was all they asked us for. Extrema, inflection points, and horizontal tangents. Okay, so I've got, the only other thing that I did was I put the points on, I put my absolute max up here, and I actually called it a point. So that absolute max was at the point 6, 34. And my relative min was at the point 4, 20. And my relative max was at the point 2, 28. And this was my absolute min at the point -5, -26. Okay, so I added those. But I think that's it. Those are, you know, it's kind of hard because you're reading, and they told you that this is the graph of the derivative, right? So, you know, you had to think about, well, if you take the derivative of the derivative, you've got the second derivative, and you're talking about concavity and points of inflection. Those are the things that you had to think about when you were drawing that. So those are a little bit tough to do. Calculus-based justification from the graph of G prime equals F. So in differential calculus, which is what derivatives, right? We use the derivative f prime to discuss properties of a function f. In integral calculus, which is the integral is what we're starting to do, we need to reverse our thinking. Our new goal is to use derivative functions to talk about antiderivatives. In the example below, we say that G is an antiderivative of f. Let's summarize the relationships between the properties of a function and its antiderivative. So, given the graph of f, let g of x be the integral from 0 to x, f of t dt. So we are looking at that as a derivative function. So f is positive on the interval from 0 to 8. So g is, and remember, if f is your derivative and you have inflection points not inflection points, I'm sorry. If you have critical points at 0 and 8, and look, your derivative, f equals g prime. Your derivative is positive here, negative and negative. Look, this is a min for your original function g, a min for g. This is a max for g. And this is increasing. G is increasing. G is decreasing. G is decreasing. Okay, because that is your derivative. So f is positive on the interval from 0 to 8. So g is increasing on that interval. F changes sign at, well, I think that they are only going to talk about this 8. So let's just say f changes sign at x equals 8. So g must have a relative, and we said maximum at 8. Since f goes from positive to negative at x equals 8. So the graph of G is decreasing where F is, where would it be decreasing? Where F is negative, right? For values of, and then that would be x greater than 8. And we do have this also, but we're kind of just looking, you know, from 0 on for this one, okay? And then the graph of F is increasing on 0, 4, because the graph of F is increasing. You have to be careful because this tells you where G is increasing. But if you're talking about F increasing, this is F, so it's increasing from 0 to 4. So please be careful when you have problems like this. So, and if F is increasing, the derivative is increasing, that means that G is concave up on that same 0 to 4. And the graph of G is concave down where F is decreasing for values x greater than 4. The graph of F has a maximum at x equals 4. So G has an inflection point there, okay? That's where the inflection point is, because it goes from being positive slopes of tangent lines to 0 to negative slopes of tangent lines. So for my G double prime, which would be my just F prime, you have that 4 as your critical point. And you would have had positive slopes on that side and negative slopes on that side. And so this is a point of inflection then for that second derivative. Okay, or for the, it's a point of inflection for the original function, but you get it by looking at the critical points of the second derivative. All right, so now, reasoning and justification summary. When the derivative function f is positive, so when the derivative is positive, think of this picture right here. When the derivative is positive, your antiderivative is increasing. So that's your original function. When the derivative is negative, your original function is decreasing. That's your antiderivative, is your original function. When the derivative is increasing, then you have concave up on the original function. When your derivative is decreasing, you have concave down on the original function, the antiderivative. And changes in sign where it crosses the x-axis on the derivative are going to be extremum points on the antiderivative. Okay, so hopefully this all makes sense with using the example that we had there. I tried to make it make as much sense as possible. I hope the audio is working.